Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with lecture 55 of our synchronous machines chapter, right? So today we will discuss about a new type of rotor construction, that is salient pole rotor. So we had already covered the cylindrical pole rotor. Now we will cover the salient pole rotor. Okay, so in salient pole, if you remember, like, what is the difference in than cylindrical and salient is, remember, it is cylindrical. Why is it called cylindrical? Because actually the shape is something like this. Like, you are just seeing the side view, this is a side view, but actually in 3D it's just a cylinder, right? It's just a cylinder where each sides are circle. So that's how a cylinder shape is made. So this is a cylindrical rotor, this is a salient pole rotor. Okay, so now the important point to understand here is that what will be the difference basically. So one important thing that we can understand is that this stator will produce its stator mmf, known as the whatever mmf due to the armature current, right? Due to the armature current, whatever mmf it will produce, right? So that will be known as the armature current, because armature current is this one only, right? The stator. So stator, due to, if it is connected to a load, stator will produce a armature mmf no named fa. Stator will produce armature mmf named fa. And I know, of course, rotor itself will produce a mmf named ff. So in case of cylindrical, we used to simply add these two mmf and we used to get our resultant mmf. And we used to deduce one thing, that we would have directly written this formula, this value, that this will be equals to same, this will be same as this equation, phi f plus phi a equals to phi r, right? In case of cylindrical, you should do it, right? If you remember, that you should do. But in case of a salient pole, can I do this? Can I do this conversion? The simple answer is no. Here I will not be able to do it. Why I will not be able to do it? Here this equation will still follow. What equation? That your FA, that is armature mmf plus field mmf, will be equals to resultant mmf. Okay, that is what my resultant mmf is equals to. But I will not be able to write it here. Why I will not be able to write it in terms of flux? Simply because, remember, your flux, right, will face two paths. Here also, let's say, like, this is, here current is incoming, here current is outgoing, right? That means if I cross my fingers, how is the magnetic field? So curl my fingers, magnetic field is going from up to down. So magnetic field, actually this should be rotated, actually this should be north to south. So magnetic field is like up to down, correct? So if it is up to down, so the bottom will be the north pole, and the top will be the south pole. Okay, bottom will be the north pole and top will be the south pole, right? So because magnetic field is going like down, from down it will follow this path, right? If you see, just I'm observing at a single instant, let's say at t equals to t naught, I'm observing this, right? Of course the rotor will rotate with respect to time, rotor will rotate, that much I know. But at a particular instant I'm observing. Okay, so if at a particular instant, if I observe, what do I get? Okay, so the flux will be somewhat like this. Okay, it will start from north, it will go into south, it start from north, go into south. Okay, this is how a flux path will take. So what do I observe? I observe here, right, the air gap is always same, that is g. C. But for the same, right, already like rotor conductors are there. Okay, rotor conductors, so we place the rotor conductors, field is already made. Now if I observe one thing, what path will the flux follow? So if I see here, right, flux start from north pole to south pole, start from north pole to south pole, right? So one thing I see, because it will link, this flux will link with the stator conductors as well. I see that here, right, the air gap is very huge. Here the air gap is huge. Okay, it is like very huge. That is, this is not the direct axis, this is the quadrature axis to the field flux. The air gap is very high here, right? So the mmf will face very high air gap here, right? So reluctance will be higher. And here if I see near the direct axis, the air gap is very small, right? This is gd. Okay, so here the air gap will be very small, gd. Okay, so now I cannot simply, because your flux, right, flux is mmf upon reluctance. So if your reluctance is changing, so will your flux change, right? And your reluctance is changing depending on where I am at, right? So reluctance is position dependent. So reluctance is position or load dependent, right? Mainly it is position dependent and dependent on the load. Why it is dependent on the load? Because what you know that if I say motor is operating in, let's say, 0.5 lagging power factor, 0.5 lagging power factor. So if I say motor is operating in 0.5 lagging power factor, then basically what does it mean? It basically means that the, what does it mean? This lagging power factor 0.5. So lagging means the peak of current waveform will happen uh, it is 60 degrees later from peak of voltage waveform. So voltage will lead the current. How can I explain this in terms of the mm, like diagram, right? So how can I explain this in terms of diagram? So it basically means like what is defined by voltage? Voltage will be decided by the main field mmf, that is ff, right? Main field mmf, and the current will be decided. So basically, what I'm trying to explain. So current will be maximum. So when voltage has already passed, right? So at this, like for this conductor, if I say for conductor A, so when will the voltage be maximum? When flux is maximum, right? When flux is maximum, then my voltage EF will be maximum, right? Correct? For conductor A, I'm talking about. So how? Because my EF is equals to root 2 pi F phi m n, right? This we already know. So voltage is directly proportional to the flux. So for this conductor A, when the flux is maximum, then the then the voltage is maximum, right? But here I am saying that the load is lagging. So voltage will lead by 60 degrees. So let's say at time t equals to t1, I'm at this position. At this position, will the current be maximum? No, current will not be maximum. Current will be maximum 60 degrees afterwards, right? 60-degree electrical. So I am not talking about that electrical mechanical thing. I'm just telling you that if the motor initially was rotating in the clockwise direction, so motor will rotate more whatever degrees in the clockwise direction to have that like it had already maximum peak voltage here, but the peak value of current will come later, right? So when the north pole reaches over here, then the peak value of current comes, right? When the north pole reaches over here, then the peak value of current comes here, right? Let's understand it is like 60 degrees electrical or whatever mechanical angle. I'm not discussing about the angle right now. Okay, so in this position, what will be the uh, field flux mmf direction? So field flux mmf direction will be somewhere here. Okay, this is the field flux mmf direction. What about the armature flux mmf direction? So if I see armature flux, actually one thing I had done wrong here. So let's assume that here the current is incoming in A and from the other ends it is outgoing. Okay, so if I take just the curl of my fingers, I see that the direction of the mmf, right, direct axis of the mmf, armature mmf, will be somewhere here. So this direction, this angle, right, between the field mmf and the armature mmf is dependent on the power factor. So more angle this will change, more the power factor will change, of course, and more like mmf has to like if it is very near, right, then it is very near to direct axis, so the air gap is very low basically here, right? It has to, it does, like the interaction will be very good. If the power factor is very high, then the interaction will be very bad, right? Because the flux has to pass through all this air gap, which provides high reluctance. So from this we can conclude, basically the conclusion is important, that reluctance of armature mmf Fa is is load dependent. Okay, so this was the important point. So here basically your reluctance, right, Fa, armature reluctance, has two components. Like one component will be a quadrature component FAQ, that will be perpendicular to field flux. Like this angle is known as the angle between the armature mmf and the field mmf. This will be psi. How this will be psi, I will explain. How this will be psi, I will explain. So this will have two components. One component will be along the field flux, okay, one component will be quadrature. So that's why the quadrature one is called as FAQ and the along field flux is called as the FAD. Okay, FAQ, FAT. Got it? Now the angle will be psi. Okay, I will explain how the angle is psi. So the along component along the direct axis, the value of that will be FAD, magnitude of FAD, direction I am not talking about right now. It will be FA cos of psi, because this angle is basically between FF and FA is psi. How it is psi, I will explain. Okay, sorry, okay, sorry, no, it is not psi. This angle is actually not psi. Sorry, I made a mistake here. Sorry, this angle is actually not psi. Sorry. So your FF, right, will lie along the quadrature of the field flux. Okay, let me draw the phasor diagram. I will explain. So for, okay, let me ignore this. Just let us understand this part only. Otherwise, you will get confused. That your armature MMF will have two components. Okay, and of course, if your MMF has two components, that means whatever current that is getting induced in the armature, that also has two components that will be along the same direction. This will be IAD, that is the direct axis current, and this will be IAQ. Okay, same thing. Okay, because we have MMF also will have current. Okay, I hope you have understood that thing. So now one key point you have to understand, that your FA and phi A will not be in same phase. Why? Because I have already told you reluctance is direction dependent, right? Reluctance can change. So reluctance is load dependent. Okay, so let's now draw the phasor diagram. Basically, how will I draw the phasor diagram? So let us first start off with the most simplest phasor diagram. So I know that my field flux is here. This is my field flux, right? Then I have my, due to this field flux, obviously how this field flux was there on the rotor side. Due to this, basically we had generated a induced EMF that will lead by 90 degrees. The field flux, it will lead by 90 degrees. Now one more thing I know, that there will be a armature current, right? For now I'm not drawing the potential VT, terminal potential VT, right? So there will be armature current IA. So this angle between IA and psi is how much? So IA and EF is xi, right? That is the xi is what? Xi is known as the internal power factor angle, and I observe that in this case it is lagging. So it is here, I have assumed that IA is lagging, mostly it will be lagging only. Okay, so now let me plot the other components. So this is my IA, and I have just told you that this IA will have a MMF, right? That is FA. IA will have its MMF, that is FA. Okay, FA. So yeah, now what can I say, what else can I say? IAFA is there. So uh, now this FA will have two components, correct? One will be along this, one will be perpendicular to this, right? So the along component will be what? The along component will be actually the quadrature one. Why it will be quadrature? I will explain just in a second. So this FA, I can break it down into two components. This component will be what? This component will be FA cos xi. And in what angle is this? To the main field flux. I see it is, with respect to the main field flux, it is 90 degrees. So that means this flux, right, is the quadrature flux. Why is it important? Why? Because if I notice this path completely very carefully, I see I kind of have two paths. One is along this path, right, that has fixed air gap similar to cylindrical pole rotor, and there is another path that is perpendicular, right, and this also has almost same air gap, and this is known as the q axis, right. That's why this mmf is called as the quadrature axis mmf, and this mmf is known as the d axis mmf. Okay, so this one is known as the quadrature axis mmf, and this one is known as the d axis mmf. So that's why we have two components. One should be quadrature to the main field flux. So I say with respect to the main field flux, this portion is quadrature. So that's why your FA, right, has this component is called as the quadrature component, FA cos xi, and the other component, if you see, you will say, sir, it is not in the same direction as the main field flux. I will agree. It is not in the same direction as the main field flux. That is your F. FD is equals to FA sin xi. Yes, it is what? It is anti-parallel to the main field flux. Still it is in the like same line, right? So this is in the same line, so it will be opposing. So it will be opposing to the main field flux FF. Okay, very important, very key point to understand. It will be opposing. It will be in phase opposition, right? So these are the important points basically. So you will have two kinds of mmf, right? So what do you know? We know due to ff. Now how do I plot the resultant mmf? So resultant mmf will still be kind of same only, right? So resultant mmf will be what? It will be basically this mmf plus this mmf. This will be same only. This will not change, but the flux has changed. Okay, this will be still fr. Fr will still be there, correct? Fr will still be there, but you cannot directly write their flux. Okay, because these mmfs will have two different components of current. Okay, so this will have corresponding to this will have a current of quadrature current, that is known as iq. So your armature current, right, will be a vector sum of two kinds of current. One is the id plus j iq. Okay, so direct axis current and the quadrature axis current. So your so one thing I know, that corresponding to your main field flux, we were getting a induced EMF EF, right? This we know, correct? So and what is the direction of the induced EMF? So the direction of the induced EMF was basically, sorry, it was not leading actually. Sorry, if I said the induced EMF will be leading, I'm sorry, it was lagging, right? Because I am rotating from the main field flux in the clockwise direction. So minus j, as it is lagging, so it will be minus j. So minus j into whatever, there will be some constant k1 into the field current, right? This will be the mmf. So like here, right, the problem here was I was not simply able to write this, right, EA equals to, like, the induced EMF due to FA, EA is equals to minus J KA into IA. This is wrong actually, right? Because this constant will not be a constant, not a constant. Why? Like, what is supposed to come over here? Basically, what is supposed to come is what? In case of a in case of like E is equals to minus J into I, basically it is we are noticing what? Lagging behavior. So it is basically reactance minus Jx into If, right? So this right, reactance is always constant. This reactance is always constant. That is what we assume. But here, right, reactance is not constant, because I told you, right, we'll have two reactants. One will be along the direct axis, another one will be perpendicular to the direct axis. So the reactance is not constant anymore. The reactance is not constant anymore. So you might have a doubt that how am I writing this? Because already, like, I am providing the EF, right? I am providing the EF, right? In the rotor field windings, EF is provided by me. Then we generate the flux, and that flux then generates a armature current, and that armature current will generate a MMF, and that MMF is what we are discussing, because field flux is already done. That is already done. Okay. So just I cannot write this equation. That is a problem. That's why I had to break it down, right, in terms of IQ and I. Sorry, this is not IF. Sorry, this is IE. Sorry, this is IF only. So this, right, I cannot write it IF. What can I write? I can write that there will be two induced EMFs. One will be FAD. FAD. FAD will be EAD. Corresponding to FAD, there will be EAD, due to which minus J. What will be the reactance? Reactance will be simply minus J into I, sorry, minus J into X, the direct axis reactance, into ID. Okay, because I know this reactance is constant, that's why I can write the equal to symbol here, and corresponding to FAQ, I will have another induced EMF, that is E. AQ equals to minus J XAQ IQ. Okay, so this equations I can write. These equations I can write, but I cannot write this equation. Why I want to write this equation? Because if you remember, we had derived expression, right, that my EF, sorry, my VT was equals to, or ER, right, ER we had derived, ER was equals to EF minus J, we had not considered the leakage reactance, right, minus J into XS into IE, right. This was the normal cylindrical rotor equation, if you remember. So the same kind of equation I want to write in our here, right, in our salient pole. How will I write that equation? So in this case, this is correct. So by adding these two vectors, I will get a resultant MMF. So if I add these two vectors, right, so I will add these two vectors. So what I can say is, what will be the resultant? Resultant will be just from here to meeting these 2 points, right? That's it. meeting these 2 points. Okay, sorry, resultant will be this, right? Yeah, so resultant will be this. This will be FR. Okay, so this will be my resultant, right? So according to this resultant field, I will get a EMF. That EMF will be 90-degree lagging to this FR. So that EMF will be 90-degree lagging. So it will be somewhere around here. This will be my resultant EMF. Okay, so this angle will be 90-degree lagging. Okay, so same kind of equation I want to write, but I cannot write it in equation. Yes, you can write this is totally valid, right? This equation will be valid still. Basically this equation is still valid because we are adding it vectorically, right? Your FR will be equals to FA plus F F, right? Your ER will be vector sum of the armature, all the of the field flux, field MMF, field EMF plus the result plus the armature induced EMF, right? EA. But I cannot convert this EA into a form like this, minus JX into XS into IA, because the reactance is different. So the because the reluctance is different, so the reactance also will be different. So I cannot simply write it like this. So I have to break it down. So I will break it down. So my ER I will write in salient pole rotor ER vector, right, will be equals to EF plus the E armature of the induced EMF in the along the direct axis plus the induced EMF along the quadrature axis. Okay, induced EMF along the direct axis and along the quadrature axis. Very important to understand. So how will I break it down now? So say I will just break it down like this, right? Here I have already written the answers. So my ER, the resultant EMF will be equals to what? The resultant EMF EF vector will be equals to this minus J XAD into ID minus J XAQ into IQ. Okay, minus JXID into ID minus JXAQ into IQ. So this will be the actually the equation that is the most important one. Of course, still we have not discussed about the armature resistance, which of course I will discuss about that. Okay, I will of course discuss about that. So like in a proper way I have already drawn it. It is here. So the proper phasor is here, right? When my IA is lagging, okay, then what are the values? What is the phasor diagram? Already I have drawn it over here, and this will be EAQ, this will be FAQ. FAQ, like EAQ will lag by 90 degrees and with respect to FAQ, and again your EAD will lag the FAD by 90 degrees. Okay, and your resultant armature MMF will be here, and your EF is here. So somewhere between here your resultant EMF will be there. Okay, that is the main thing. So what will be, how will you draw it in the phasor diagram? How will you draw it in the phasor diagram, and yet I have not considered the drop, IARA drop, right? So we have to consider the IARA drop as well, right? So now this analysis was with RA equals to 0, right? Here there was no armature resistance was 0. Now we will do the exact analysis where armature resistance also will be there. So armature resistance is constant, right? Like the path of the armature windings, like this is the resistance of the armature, that is constant, right? That is not like load dependent or something, right? So armature resistance is not equal to 0, which is constant. So if it is constant, what will happen? What will actually happen in the equation, right? Your Vt. Now I am writing Vt. I'm not writing EF. I'm directly writing Vt. Also, one more thing, what will happen to the like Vt, like if you remember the phasor diagram, right? The phasor diagram was somewhat like this. If I draw the phasor diagram over here, so here I had EF, then I had a variable reactance that was basically XAR. Okay, then this point is known as the, after removing this is XAR is due to the armature reaction, I get my resultant EMF, and then we consider our RA and our leakage reactance XL, right? This will always be there no matter what. No matter what, leakage reactance is how much flux is getting leaked out. So no matter what, if uh, like I'm following through the direct axis or through the Q axis, leakage reactance will be there in both the paths, both in the direct axis and the quadrature axis, right? So leakage reactance will always be there together. Okay, so the thing is, this will automatically get added to both of the reactance, both the direct axis reactance and the synchronous reactance, because leakage reactance will always be there, and here this is my terminal voltage Vt. Okay, so that part is I hope clear. So your XAD will be equals to XAD dash plus X leakage. Okay, leakage reactance will be constant throughout, it does not matter, it mainly depends on the flux linkage, right? Okay, so leakage reactance will be constant throughout, and your XAQ also will be a combination of quadrature plus XL. Okay, quadrature plus XL. Okay, so now what I can say, now let me draw the phasor diagram actually. So if I draw the phasor diagram, like what, before drawing the phasor diagram, let me write the equation first. Okay, so what will be my Vt basically? What will be my Vt? So Vt is equals to EF vector will be there minus IRA, this will be there, this drop will be there no matter what, right? Armature resistance is constant, it does not matter, minus J into IA into XAD plus X leakage, this I have to consider, right? XAD dash. Okay, this is the direct axis, so this will be not just IA, this will be IAD, this will be IAD. Okay, only the direct axis current will totally be added with the reactance, right? XAD IAD. Okay, minus J IAQ into XAQ dash plus XL. Okay, so yeah, this will be basically my Vt. So now like this, right? We don't write it always, like they don't show you, they don't directly show you, Okay, they directly write this equation. IA RA, you will not you will never see this equation. No one will write this equation. Minus J, they will directly write this ID into XD minus J IQ into XQ. Okay, so yeah, so uh, now can I draw the write the phasor? So one key point is, if I have like one important point, if like I'm not drawing the equivalent circuit here, right? So I will have two reactances. One will be XAD dash, another will be XAQ, right? And it is just basically, actually they are not parallel. Okay, in real life they are not parallel, just I'm representing them. And if a, like this circuit, right, it is just a black box, assume it as a black box, and I have it like it is just a salient pole rotor, right? Okay, and here I have a series reactance X connected. So what will be the equivalent direct axis reactance and what will be the equivalent quadrature axis reactance? Can you tell me in the comments? Pause the video and tell me in the comments below what will be the equivalent direct axis reactance and the quadrature axis reactance. Or let's say if I have more reactance, let's say here I have more reactance x1, x2, then they are parallel, right? So what you do is you find out the equivalent reactance on the right hand side, okay, of this salient pole rotor. That equivalent reactance will be xeq, and your direct axis reactance, overall direct axis reactance will be xad dash plus x eq. Okay, so yeah, xad dash plus xeq, and your quadrature axis reactance will be x aq dash plus x eq. Okay, yeah, x eq will be x eq dash plus x eq, and x ad will be x ad dash plus x eq. Okay, so this both of them will be added. So this is a very important point for you to note. Okay, now let's come back to the phasor diagram. How will the phasor diagram look, right? So the phasor diagram will be very simple. So I will have, first of all, I will draw the phasor diagram here. Okay, it is already drawn over here. Okay, let me draw it, otherwise you will get confused. So let me draw it briefly here. Okay, so this is my EF, and this is my let's say IA. IA. So from here, first of all, I have to do minus IRA. So minus means just in the opposite direction, right? From EF. So just I have to go in the opposite direction of EF, minus IRA, right? So let me do one thing. So this is psi, right? Let me do the minus I array later. Let me do this first. Okay. So what is ID basically? ID will be, if you remember, what was ID? ID was here, right, along this direction, that it is 90 degree perpendicular to EF. So it will be IA sin xi. So ID will be in this direction. Okay, ID will be in this direction, right? Let me color this. Sin xi. Okay, so this is my ID basically, and I have to do minus j. Minus j means what? Minus j means rotate in the clockwise direction. Okay, let me, okay, so let me do the IQ first, because I want to explain one thing. So that's why it's better we do IQ first. Okay, it's important we do IQ first, otherwise like it will just be a mess up. That's why. So IQ will be in this direction, right? So this will be my IQ along the direction of EF. Let me write this ID only. So what is this? Minus j into IQ, right? Minus j means rotate in the clockwise direction, right? And then add with EF, right? So rotate in the clockwise direction, that is, if I take this vector and if I rotate in the clockwise direction, so not minus 90, it will be, yeah, minus 90. Clockwise means minus 90, and I have to multiply a constant term, that is x cube. So that will give me this I cube minus j into IQ x cube. Okay, and I have to add that vector with EF, right? So why I did not do it, I will explain just in a second. Okay, now I will do the same with ID. So ID I have here, I will rotate this in the clockwise direction and multiply xd, right? So this will be my minus j minus j id into xd. Okay, now what I will do, again I have to subtract minus IRA. So IA is in this direction, minus IA will be in this, just in the opposite direction, correct? Just minus 1 means 180 degree, right? So minus 1 will be 180 degree. So this will be minus IARA. Why I did not do it? Because like actually finally the resultant will be here only, right? Like it does not matter if you do minus IRA first, then you do minus j x j. Ultimately you will reach this position only. Okay, but this looks more elegant. Okay, that's fine. That's fine. Okay, so this is, remember, this is for a lagging load. Here will be my resultant terminal voltage VT. This will be my resultant terminal voltage, that is VT. Okay, and the angle, this angle will be known as the power angle delta. Okay, so yeah, that's how you solve this basically. Okay, that's how you solve the phasor. So here is the same phasor here, same thing, whatever I have done there, same thing I have done here without IARA. Okay, I should have done IARA as well. Okay, missed it. So IARA also will be there, because there will be a drop of the armature resistance. So I will basically, so here I actually had done it opposite meaning now I am traveling from VT. Okay, this one way you can understand it like this: from EF I am traveling, EF I am subtracting these vectors, right, adding these vectors whose magnitude are negative, so that's why there is negative sign. You can write this equation in other way around as well. Okay, this V has gone away, so this will be, I can write that my EF will be what? It will just be opposite, VT plus IRA plus J IAD XD plus IAQ XQ. Okay. So here, right? So now I will travel from VT. So VT will have a component named IRA. That component will be there. So IRA this time is plus, right? So it will be along the same direction. So IA RA. Okay. And then I will add this component, that is plus j IAD XCD. So IAD will be in what direction? 90-degree black. So this thing you have to always, like, you can, if you can remember, it's good. If you cannot remember, right, just do one thing, just write the flux. That's it. Write the flux. So your IA is here, okay, and your psi will be here. And you know that the MMF along the direction of EF will be what? Will be quadrature. Why? Because FA is actually here. Sorry, FF is actually here, right? This is my FF, correct? So so here is my component along the direction of the EF, that is quadrature to FF. That means this will be what? This will be FAQ. So FAQ will give me IAQ. So that's how you remember, right? That's how you remember this thing. So always remember that IQ will be, how to remember, I have already explained, right? IQ will be in phase with F AQ, and your ID will lag EF by 90 degrees. Okay. So yeah, so yeah, that is the case over here. This thing you can remember. So this will be what? So ID will be here. So here IAQ is here, and here I have ID, right? This direction is ID. So J into IAD, this time plus J. Plus J means anti-clockwise, plus 90. So it will be anti-clockwise. So this will be my direction of plus J ID into X ID, and then plus J into IAQ. So plus J means again anti-clockwise. So this will be the direction of IAD. So yeah, this will be IQ into XQ, and this will be ID into XD. Okay. So yeah, that's how you can draw the phasor diagram. Okay. So both ways will work out, and this equation is the most important one, and I hope all the conclusions are clear to you. Now again, if I want to say what is the what is this psi angle, if I want to compute this psi angle, right, how will I compute this psi angle? So I can break this down again into two components, right? If I see this IRA, right, this IRA and this, right, will have what angle? IRA and this is parallel, right? So this angle will be what? This angle will be psi. Okay, because this is same psi. Okay, these are parallel to each other, although it does not look like that, but these are parallel. So this is psi and this is also psi. This is parallel. So this will be psi. So now let's understand how can I write this value. Basically I want to write what is my tan psi. Okay, and what is my EF? Those values I want to calculate. So let me, like, trust me, this analysis, right, you will not get anywhere. You search anywhere, everyone will explain with something else. I am explaining, like, you go and like, if anyone has studied already, right, synchronous machine, then I know there will be a bit of confusion of the derivation of the tan psi. How has the derivation came? So I will just take this with me. Okay, I will just copy this thing with me and paste it over here. Few things I have written it down, I will explain to you, right? So if like this is my this was my IA over here. Okay, and this was my xi. Okay, so if this is also xi, right? So these are parallel. So this is parallel. So this also will be xi. Now this is xi. So this also will be xi. Now this is xi. Okay, this is xi. What about here? So here again I will draw a parallel line. So this will be xi. Okay, if I extend this line, this will be xi. This will be how much? This will be 90 minus xi. Okay, now I will break down the components. So I actually want to write down the components, right? So I will have two components. I want to write along IA and perpendicular to IA, right? Perpendicular to IA. So for the EF portion, along IA, what is the value? Along IA, that is EF cos xi. Okay, and perpendicular, what is the value? That is EF sin xi, right? If I take the ratio of these two, I will be able to get my tan xi value. That is the important portion to me. One more thing is important here, that my xi is equals to what? Xi is equals to, for a lagging load, this is delta, right? This is Vt. So it will be delta plus theta for a lagging load. Leading load, you just replace theta with minus theta. That's it. Leading load, you just replace theta with minus theta. Okay. Now here the important portion is that I want to understand how you can write this, right? So now I want to break it down. So this portion I am done. So left hand side I am done, right? So what about the right hand side? Right hand side, this is what? This is Vt. This much angle is how much? Theta, right? Angle between the terminal voltage and the armature current will be theta. So this one of the components will be Vt cos theta. Now I have to break down the other components. So I see this IRA is just along Vt cos theta. This IRA is just along Vt cos theta. Okay, IRA is just along Vt cos theta. So this will be plus IRA directly, right? There will not be any component. This will be plus IRA directly. Now let me break these components down, right? This XD and IQ XQ. So this ID XD has two components. One will be along the xi, along IA, that will be ID XD cos of xi. Okay, I'm just writing C xi for short form. And other component that will be perpendicular in this direction, that will be ID XD sin of xi. Okay, these two components. Now this also will have two components. One will be along here, one will be along here. Okay, so along this component will be IQ XQ. Remember, this is just in the opposite direction of IA. So I can actually write this over in this side as well. How will I write it? So I will write this, right, in this direction, but I will write negative because actually it is supposed to be in this direction, right? So if I am rotating 180, just a negative sign I will attain. Okay, so minus into IQ XQ into what is this angle? This angle is 90 minus xi. This angle is 90 minus xi. Okay, this angle is 90 minus xi. So cos of 90 minus xi is sin xi. So this angle will be sin xi. Okay, and the perpendicular component will be again in the same direction only, in this direction only. This will be what? This will be iq xq into, like, remember this is 90 minus xi, so this will be sin 90 minus xi, that is cos xi. So this will be iq xq into sin 90 minus xi, that is cos xi. Okay, so this is what I have written here. So idxd cos xi, idxd cos xi is along ia, so this is, these components are along ia, along ia. IQ cos xi, no, IQ sorry, this is I, so this is along ia, this, right, and these components are perpendicular to ia. Okay, that is id xd sin xi. You see, id xd sin xi is perpendicular to ia, and id xq cos xi is again perpendicular to ia. Okay, so what I can notice over here is that the important points to notice over here is this thing, that here I will make a approximation. Okay, this you have to make, this approximation you have to make, otherwise you will not be able to solve it. Okay, like this is the final value, this you can add directly. So basically actual value of tan xi is what? Actual value of tan xi is this, which you will not see in any book. Nowhere in the book this value will be written. Tan xi will be equals to, like, what is the parallel component along ia? This vt cos theta plus ia array plus these components, right? These are always parallel. So this is ia sin xi cos xi xd, ia xq sin xi cos xi, right? So this is, so divided by basically vt cos, so this is basically ef cos delta. So I will write this ef cos xi. So this component, right, ef cos xi component along ia, ef cos xi will be equals to vt cos theta plus ia array plus this value, okay, ia xd sin xi cos xi, ia xd sin xi cos xi sin xi cos xi, and there is a negative sign. If you see, there is a like this, right, this vector is actually opposing, right? This is in this direction and this is saying in this direction, opposite. So that's why there is negative iq xq sin xi, that is basically equals to iq x ia xq sin xi cos xi, because iq is, like, I have broken down my ia in terms of iq and id, right? This much you know how to break it down. Okay, broken down my id in terms of ia and xi. Okay, so ia sin xi will be id, ia cos xi will be iq. Remember this, right? So that's why I have put iq equals to ia cos xi. That's why this become cos square xi, and here it become sin square xi. Okay, that thing I have done. So this will be minus ia xq sin xi into cos xi. This is my ef cos xi. What is my ef sin xi? So my ef sin xi is actually equals to this. First of all, again same, right, vt sin theta, vt sin theta will be there, of course, perpendicular component, plus now this ia array is gone, ia array is not there, but what are the other components? These two components are getting added, that is these components and this component. So ia xd sin square theta plus ia xq cos square theta. So ia xd sin square, not theta, sorry, xi plus ia xq cos square xi, correct? Okay, so yeah, So now actually tan xi is this divided by this, but here we actually make few approximations, right? We assume xi to be low, we assume xi to be low value, xi to be near 0. Okay, here we have to make it this approximation, right? If I assume xi to be near 0, then your sin xi will roughly be 0 and your cos xi would roughly be 1, right? Roughly. One more thing you have to remember, that the value of xa and xd actually varies. The value of xa and xd varies actually. So roughly they are actually equal to each other, that's why they will cancel. This will almost be equal to this value only, almost this will cancel in, if you, even if you don't do approximation, almost they will cancel out, almost. You will see this. Okay, this you will see. Now if I assume, if I do this assumption, then what happens, then basically my tan xi becomes vt sin theta plus, remember cos xi is almost 1, this is almost 0, so this will be only ia x cube divided by vt cos theta plus ia ra. Okay, because here both sin xi is there, so almost they will go to 0. Okay, so we can neglect it. So it is better if you are able to remember this formula, because this might be useful. So it is better if you are able to remember this formula. And what will be my ef, basically what will be my ef value? So my ef value, this will be equals to again this square plus this square, right? So sin square cos square xi will become 1, so this will be ef only. So ef will be equals to under root of vt cos theta plus ir whole square plus vt sin theta plus ix cube whole square. Okay, so these two formulas, if you are able to remember, that's good for you. Okay, now let's derive this same thing for the leading load. How will I derive it for a leading load? So for a leading load, you just have to replace theta with minus of theta. Okay, you just have to replace theta with minus of theta, so then you will be simply sorted. Okay, so here if I replace, yeah, theta with minus of theta, so this is for lagging. For leading load, what you will do? For leading load, replace theta to, like you can derive, derivation is homework for you, right? Derivation is homework for you, please derive it by yourself, that is the homework. Theta 2 minus theta, if I replace theta 2 minus theta, this will be actually, here my xi was delta plus theta, here my xi will be just the opposite. Okay, it will be like your tan of xi, that is tan of delta minus theta will be equals to, if I replace theta with minus theta, this will become sine of minus theta is minus of sine theta, so this will be minus of vt sine theta plus ia x cube. Okay, this divided by Vt. Cos of minus theta is cos theta only plus Ia Ra. So if I multiply minus on both sides, what will happen? This will get converted. Tan of theta minus delta will be equals to, because I want to make Vt positive, right? That's it. So Vt sin theta minus Ia xq divided by Vt cos theta plus IRA. And what will be the EF magnitude this time? EF magnitude. EF magnitude will be under root. Just one difference will be there. This will be same, right? Exactly carbon copy. Just a negative sign will be there with sin theta. That's it. Okay. So here negative sign will be there. That's it. Okay. So this is what your EF will be for a leading load generator, right? Unity power factor is very simple. Unity power factor, this will be 0. So only this much will be there in the top and in the bottom. So for the unity power factor, UPF, right? You make theta equal to 0. Replace theta equal to 0 in any of the formulas, both will work. Replace 0, theta equal to 0 in any of the formulas, both will work. Okay. Now, what about motor? For motor, what you will do? For motor, how will you solve it? So for motor, what you have to do is, I will do one of them. Okay, for motor, it's the same only, but here you have to replace Ia with minus Ia. That is the difference. You have to replace Ia with minus Ia. So in case of motor, what is my Vt equals to EF minus J minus IRA minus J IQ XQ minus J ID XT. Okay. Minus J ID into XT. Okay. So now what I can do? Okay. So IRA yeah. So here if I draw the phasor diagram, right, this time with respect to Vt again I will draw, because I want to draw EF. This time EF will lag Vt, so Vt will lead. So this time this will be my Vt, because Vt is the reference. From the bus bar I am getting the voltage Vt, right? So this is my Vt. Okay, and assumption is, let's assume that it is a lagging load. Okay, so if it's a lagging load, right, Ia will be somewhere here. This will be my Ia basically. Okay, and this is my theta, and this will be my EF. EF will lag. How it will lag, I will show you. So basically this time, okay, if I write my EF, right, sorry, okay, I have written it totally wrong. Sorry, I'm really sorry. So sorry, I'm really sorry. So this is my bus bar, right? So from bus bar Vt's angle is coming. So here there is that armature reactance plus whatever Ra is there, right? So this resistance is there. Then I have the motor basically. So with Vt I'm subtracting everything. I have just written the same equation as motor. I'm sorry. Here, right, if you see, I have just written the same equation as motor. I'm really sorry what I was thinking. So if I take on this left hand side, it is the same equation. Sorry. Here it will be just the opposite, right? So Vt will be this plus IRA. So or what I can do, I can replace Vt and EF. So EF will be Vt minus all this, right? Previously it was plus. So I have to subtract IRA, right? So if I subtract IRA, or let me first do this again for better simplification purpose. I guess IQ into XQ will be the better one, right? So again, this is IA, okay, but I have to draw EF. If I don't draw EF, this will not work. That is the thing, right? I have to draw EF. So let me assume that I have EF here, okay, somewhere in between. EF is lagging here somewhere, okay, and this is the internal power factor angle with respect to EF, xi, right? This is my EF. So what is delta? Delta will be this. This time remember, EF is lagging Vt, okay. So what I can say is that my psi this time is theta minus delta, okay. This is same as the leading case of motor, okay, sorry, of generator. So leading case of generator is same as lagging case of motor. You will see, you will observe, but you have to replace Ia with minus Ia, okay. So here if I see that again, this Ia will have two components, right? One will be perpendicular to EF, one will be perpendicular to EF, another one will be along EF, right? So along EF component will be what? The quadrature axis one. So along EF I will have a current that is IQ, Ia sin xi, that is IQ, right? And perpendicular to EF I will have ID, right? This we have already discussed. Okay. So this we have already discussed. Ia cos I and Ia sin I, right? IQ and ID. So if I am what I want to do, I want to subtract from Vt IARA. So IARA will be somewhere here. I don't want to go here right now. I want to do this IQXQ, right? IQXQ is there, minus J IQXQ. Minus J means clockwise in the 90 degrees. So I have to rotate this vector by 90 degrees. Okay. So okay, this is the parallel direction of IQ, right? Parallel direction of IQ. I have to rotate this by 90 degrees, minus 90 clockwise, right? So this will be here, and this will be my IQ. Okay. Now I have ID over here. ID. Okay. So this ID is here. Again I will rotate this ID vector by clockwise. This will be my IQ minus J IQ into XQ, okay, and this will be my minus J ID into XD, okay. This will be my, so perpendicular to this. So this is my, basically this direction is my ID, right? This direction is my ID, okay. These are not same angle, okay, remember these are not same angle, but I have to rotate another 90 degree, minus 90. So this will be my ID into XD basically, okay. Don't go by the drawing, my scale will be wrong, okay. So this will be my minus J ID into XD, okay. Now last part is minus IRA, okay, minus IRA, right? So IA is on this direction, minus means just opposite, opposite means minus 90 here, okay. So my EF, okay, Kind of it is wrong. Actually, yeah. What should have happened? I will tell you what should have happened actually. So let me just shift this. So this will be somewhere around here, I guess. Okay, like drawing is not up to scale, right? This will be somewhere around here, and ultimately I have to connect these things, right? So somehow we have to manage. So yeah, now it is opposite. Now if I make this length small, okay, just bear with me over here. How can I, yeah, how can I connect this? Okay, so this here it is connecting. Okay, of course it will not be up to scale because we have assumed few things, right? So yeah, so this is my, so this is my ef is here, and this is my ia. Are okay. uh, so yeah, so again if you do the derivation, right, you can find out like there will be two components. So again what will be your ef cos I, this time I will be fast, ef cos I, right, it will be uh, remember this is negative, right? ef cos I, this is negative, so minus IRA will be there, and before that this vt into cos theta, vt cos theta also will be there in this direction, right? I'm directly doing it, I'm not explaining it. Vt cos theta minus IRA will be there, right? Because it is along the same direction, just in opposite, that's why minus. What else is there? So again if you see, these components will be there, sin I cos I, automatically they will be cancelled, automatically they will be cancelled. So only this component will be left out. Why? Because you will assume that psi is almost equal to 0, so sin I will be almost equals to 0, cos I will be almost equals to 1. Okay, these are the assumptions that you will take. Now what will be your ef sin I? Again ef sin I, first of all the perpendicular component will be vt sin theta, vt sin theta. Now what will be the other component? So other component, if I see, this iq xq is in the opposite direction, right? It is in this direction, iq xq is in the opposite direction, so that's why there will be a negative sign over here. So minus iq xq. So I'm directly subtracting the iq xq because I'm neglecting the xd part. Okay, you see xq is in the opposite direction. Previously if you notice, this iq xq was in the same direction as your ef cos delta. Like here, although you see that like they have very huge angle difference due to theta, right? But this and this one were in the same direction. Okay, and here this and this are in the opposite direction. That's why it is minus iq xq. So from here I can directly say that your tan I will be equals to vt sin theta minus iq xq divided by vt, remember I is equals to theta minus delta, vt, I will summarize, don't worry, cos theta minus ia ra. What about the lagging case? For the lagging case you just replace theta with minus of theta. So if you replace theta with minus of theta and also your ef, right, ef will be equals to what? ef will be the same value, right, this whole square basically. So we'll write ef over here. Okay, so this is my ef. Now these are lagging. For leading, what will happen? So let me summarize, then I will explain. Okay, so let me summarize for the two cases, right? For few cases here. So summary, I will make the summary. Summary will be, first of all, the power factor. Power factor. What kind of power factor I am connecting? Okay. Then it will be, what is the value of xi? It is negative or positive? Oh, okay. No, I cannot do it, right, because things are changing. So then it will be for generator. I will write the formulas, and for motor I will write the formulas. Okay, this will be easier for you to remember. Okay, so first of all, it is lagging. First one is lagging. So lagging in case of generator, we just derived that my, like, I will copy this. I will basically copy this, right? Tan xi here, right? I will just extend this a bit. This was for the lagging case. This was for the lagging case, because this also will include the xi value tan theta plus delta. Theta plus delta, and EF value will be this. Okay. For motor, what will happen? For motor, this will be the case of generator leading, and you will replace IA with minus IA. So for motor, what will happen here, right? This will become leading, so this will become minus of delta. Okay, if you see here, right, also this is actually your delta is theta minus delta now, theta minus delta. So actually, sorry, your xi is theta minus delta, so theta also has become negative basically. So this will be, theta will be opposite basically, because IA has become minus IA, right? That's why IA has become minus IA. So this will be delta minus theta. Here what will happen? This will be minus IQXQ, and this will be minus IRA. Okay, that's it. Here if you see, same thing we have done, right? So just similar to leading case, right? Because in the leading case there was minus here, and here why I have minus? Because it is a motor, so that's why IA was replaced with minus IA. Okay, or you can remember them separately, that's also fine. That is also totally fine. For leading case, what will happen? Leading case, you will just for leading case, you will just replace your theta with minus theta. So if you replace with theta with minus theta, this will become delta minus theta, remember. So theta minus delta here, right? This has become theta minus delta, right? So and this will be simply negative here. Okay, everything else will remain same. This will be negative, that's it. Okay, and here what will happen? Here also the same thing, because you will just replace theta with minus theta, so this will become plus now. This will be plus. Okay, So IQXQ will be plus now. It will not be negative. It will be plus now. But this will be still be negative because your IA has been replaced to minus IA. Okay. This will still be negative. And for unity power factor, I hope you can do. For unity power factor, you just make theta equals to 0, right? That much you can do. For UPF, I'm not writing the results, but I hope you can do it, right? For UPF, you just make theta equals to 0 degrees. Okay, that's it. That's it basically. Okay, so that was about the reluctance and all those things. So of course there is summary. I will explain the summary as well. But before that, also let us calculate the power basically. If I want to calculate the power, how will I calculate the power? That also we want to see. It will be very difficult for us to calculate. We will not calculate in today's lecture, or we can calculate in today's lecture as well. That is not a problem. If I want to calculate the power, how will I calculate the power basically? Let me calculate for a generator. Okay, so let me take a case here. And assume that armature resistance is 0. If I don't assume armature resistance to be not to be 0, then the calculation will be very difficult. Okay, so we have to assume that RA is 0, and we have this box here in which RA is 0, armature resistance is negligible, and this armature reactance and synchronous direct axis reactance, all those things are there. Okay, all those things are basically there. Okay, so here if I write this, that this E F angle delta, and this is VT angle 0. Okay, and some armature current IA angle theta with respect to the VT is flowing. Okay, so first of all, let us assume it to be a lagging current only, although it does not matter, but let us assume it to be a lagging current, right? So if I draw the phasor diagram again, so this time as it is a generator, so this will be my EF, okay, this will be my IA over here, and this will be my VT, this will be my theta. Okay, this will be my xi, and this will be my delta. Now how do I find out the power consumed? What is the power output? Output of generator. How do I find out the power output of generator? Okay, so power output of generator, basically this, remember this IA current will have two components, right? One will be perpendicular to EF, that is ID. Another one will be along EF, that is IQ, right? And we know, how do I find out the power? Basically I find out the power, that is V into I into cos of theta. What does it mean basically? This means that the current and the voltage which are in phase, multiplied by the cosine of that angle will give me the power basically. So I have to find out individual powers. So this time my power, right, power will be addition, like this current will provide, this will have some theta, theta d, okay, this will be some theta d. What is this theta d basically? What is this value? Let me write it theta d for now, and this will be angle between the voltage and current, this will be theta q. Okay, remember cosine will be always positive because theta is between minus 90 to plus 90. Okay, so power will be addition of two powers. One will be PQ plus PD. Okay, so PQ will be, so this will be VT cos theta Q into IQ, right? And what is cos theta Q? So sorry, what is theta Q? So theta Q I can observe, it is simply equals to delta, and theta D is equals to, what is this theta D? So this, right, is equals to, how like calculate this? So this whole is 90, this whole angle is 90, right? Okay, okay. So I have to find out the angle between IA and ID. Sorry, not IA and, yeah, IA and ID only. So VT and IA has this angle. This whole angle is 90. Yeah, this whole angle is 90. This much angle is delta. This much angle is theta. So this will be what? This will be 90 minus delta minus theta. So theta D will be 90 minus delta minus theta, right? So this is what psi, right? This simply psi. Psi is delta plus theta, and I have to subtract by 90 so that I will get my theta D. Okay. Okay. So this will be PQ will be what? PQ will be VT into IQ into cos of theta Q plus VT into ID into cos of theta D. Now basically VT into IQ into cos of theta Q, right? So what is IQ into cos of theta Q? That is what I want to find out. Okay, or what is VT cos of theta Q? So VT cos of theta Q is VT cos delta. So this is basically VT cos delta, right? Theta Q is simply delta into IQ plus this is VT ID. So let me keep the ID. This is what? This is simply cos theta D is 90 minus theta. So 90 minus theta minus D. Sorry, yeah. Or I can write 90 plus theta plus delta. So this will be 90. This will be 90 VT into cos of 90 minus xi, that is sin xi, sin of delta plus theta into ID. Okay, so yeah, these are the values basically. Theta plus delta into ID. Am I doing any mistake? I just want to check this. This is ID, right? This is theta D. So theta D. Oh, sorry. I had made a mistake. Sorry. So this is theta d is this, right? This much is delta. Sorry. Theta d is this much actually. I thought theta d is this much. Sorry. So this will be only be delta here. No, theta will not be present actually. Sorry. So only delta will be present. Sorry. This will be only delta. Sine of delta. Sorry about that. Now one important thing. Just hold on a second. Give me 1 second. Okay. One important thing to note here is, of course, how is this EF made? Again, I will go back to the same phasor. This time RA is 0. If RA is 0, right? Again, the same fundamental equation. EF will be equals to what? VT plus J ID into XD plus J IQ into XQ. Okay. So ID into XD, right, plus J. So ID is here. So I have to do plus of this, right? So plus of VT. Or what I can do, I can swap this because I want to write in terms of EF. I want to keep VT constant because VT is already here, right? I want to write in terms of EF. So I will replace this, right? Exchange this over here. This will be EF minus J ID into XD minus J IQ into XQ. Okay, so I have to do minus J ID into XG. So ID is here, minus J means clockwise. So I have to subtract from EF along this direction, right? This will be minus J ID into XD, and this is minus J IQ into XQ. So minus J IQ into XQ, minus J means in the clockwise direction. So in this direction I have to move. Then I will reach my VT basically. So if I move in this direction, right, minus J IQ into XQ, then I will reach VT. So what do you notice? This VT, right? There are two components of VT. One is VT cos delta. So what is VT cos delta? So VT cos delta is basically equals to this EF minus ID into XD because this is magnitude, right? So VT cos delta is equals to EF minus ID into XD. And your VT sin delta, if you see your VT sin delta is equals to what? VT sin delta, this perpendicular component is IQ into XQ. So this is equals to IQ into XQ. Okay, this much is clear, right? This much is clear. Now I will just do one thing. I will just replace IQ and ID, right? Because here only IQ and ID are unknowns. So what is my ID from this equation? ID from this equation will be equals to VT cos delta minus EF minus VT cos delta divided by XD. Same in case of IQ. IQ will be VT sin delta divided by XQ. Okay, so now I can write what is the power developed basically. So this power developed formula here, right? VT cos delta will be there, IQ I will replace. So this will be VT cos delta into IQ. IQ is here, right? So this is Vt sine delta divided by x cube, okay, plus Vt sine delta into id. So id is this value, ef minus Vt cos delta divided by xd. Okay, so P will be Vt square sine delta cos delta by x cube. Okay, so this will be Vt square sine delta cos delta divided by x cube, plus again here also Vt square sine delta cos delta divided by xd, plus this term, this is something familiar, right? This seems something familiar. Vt ef by xd into sine delta. This seems something familiar, but this is not familiar, right? Okay, one more thing, this will be negative. Okay, so if I just rearrange my terms, and this formula you have to remember, okay, this one you have to remember, unfortunately there is no other option, right? There is no other option than to remember. Remember, this is single phase power, so per phase power. This expression will be same for motor as well. Okay, this will be equals to Vt ef by xd sine delta. This is something familiar, right? Vt ef xs sine delta, something similar to that in case of a cylindrical pole rotor, plus, now remember, this is sine delta cos delta, right? So sine delta cos delta, if I multiply divide by 2, it will be 2 sine delta cos delta. So 2 sine of 2 delta. So Vt square, if I take common, right, this will be sine of 2 delta divided by 2, right? So Vt square, if I am taking common, and sine of 2 delta by 2 if I take common, this will be 1 by x cube minus 1 by xd. Okay, so this is the formula that we are getting. Okay, so what I wanted to have a conclusion here. So one thing I notice is even if my EF is 0, so this is important actually, this formula is important, this you have to remember. Okay, no other option, this you have to remember, and remember it is per phase power, right? Per phase power, don't forget this, it is per phase power. Okay, so now what I can say is, if I notice one thing, if my EF is equals to 0, then also my power, right, developed power is not 0. How is it possible? There is no excitation, still it is able to develop. So without excitation also I will be able to develop power. This was not possible with cylindrical pole rotor because their formula was only this much, right? That is possible due to this. This torque is known as reluctance torque. Okay, I will explain what is reluctance torque just in few slides. Okay, so what is torque? This we call reluctance power, right? And the torque developed will be reluctance torque. What will be torque? So torque, right, will be what? It will be simply 3-phase power divided by omega s, because the rotor is rotating by omega s. So this is single phase power, right? Single phase power. Three phase power will be 3 multiplied by this. So this copy it, this will copy paste and multiply by 3. 3 by omega s. Okay. So if I just like further like break this down, right? So this will be 3 by omega s multiplied by this, right? Plus 3 by omega s multiplied by this. Okay. So this torque is known as the, this power is known as the excitation power. Excitation power. This is happening due to the field excitation, right? And this power is known as the reluctance power. Here this torque is known as the excitation torque. And this is known as the reluctance torque. Okay. So this torque is happening due to a phenomenon known as reluctance, right? What is reluctance? Because basically here the reluctance of the MMF is changing. Due to that, a torque is there. Okay, that we'll discuss obviously. So this is whatever we have discussed, same thing is written over here. You can go through this. In cylindrical rotor, we have a thing XS, because the air gap is constant, hence the reactance also is constant. But in case of a salient pole machine, the reactance is different because there is non-uniform air gap. Basically the air gap is not same, right? If the air gap is not same, that means it is a non-uniform air gap, correct? So the consequence of this is my air gap of the q axis, basically perpendicular to the direct axis, will be higher than the air gap of the direct axis, right? So GQ will be higher than the GD. So my reluctance of q axis will be higher than reluctance of d axis. My flux will be lower because flux is mmf upon reluctance. So flux mmf is constant because it will produce some constant amount of mmf, right? So flux will be lower in the q axis because reluctance is higher, and flux will be higher in the d axis. Now if flux is lower, inductance will be lower because my inductance is what? It is phi I, something like this, right? Inductance is simply phi into I, correct? If you remember it properly, it is phi into I basically. Okay, so yeah, it is proportional to phi. So if flux is lower, inductance will be lower. Now if inductance is lower, reactance will be lower, xq will be lower. Okay, so this is another important relationship that you should keep in mind, that generally the xq will be lower than the direct axis reactance, and that makes sense. This will have higher reactance because due to this only the main field is getting produced. Okay, so same thing, I've compared these things here, same thing is written over here. Okay, so it is also known as two reaction theory. Why two reaction theory? Because I have two reactants, one is along the direct axis, one is along the q axis, quadrature axis. That's why it is called as the two reaction theory, where we approximate. Again, this is not the exact, like still we are doing few approximation. If you remember, we had derived the formula of tan xi, we approximated it. So still there is some sort of like what do you call, some sort of approximation, right? So again we come back to this torque we have already discussed. Reluctance torque. What is reluctance torque? Due to this saliency, an additional torque component arises that is known as reluctance torque. Okay, it is independent of field excitation. Here it does not have any field excitation term. This is operating principle of reluctance motor. We will discuss about reluctance motor at the end in the next chapter, where we will discuss about single phase motors. So this principle will be used in reluctance motor. Okay, so we will see we will understand what is reluctance torque. Okay, so again, what is the what is a reluctance motor? Reluctance motor is just a synchronous motor which operates without continuous field excitation. So if I don't give any field excitation, still there will be some torque developed, and that torque is known as reluctance torque. Motor will still rotate in the same constant speed, but obviously torque will be lower, right? Because this component is not there, so torque value will be lower. Cost will be economical. Okay, maintenance will be low because it is low maintenance, because it will be a small motor. Okay, construction will be very simple than normal synchronous motor because there will not be any field excitation. Okay, in small places, right, like timers, clocks, okay, electric meters, these reluctance motors are used. So let's understand what is reluctance torque. So reluctance torque arises from magnetic property that flux lines prefers the path of the minimum reluctance. This phenomenon is leveraged in machines like switch reluctance and synchronous reluctance motor. So basically what is happening is, if I have a north south pole here and if I have this rotor, so again if you see here, the reluctance is lower, here the reluctance is higher. So flux lines initially will start here, but flux lines will not go here. They will try to come here, right? Only follow this path, the lowest reluctance path. If flux lines are falling, and this is, let's say this is north pole of the rotor. How can I make it backwards? This is the north pole of the rotor and the south pole. So what will happen if I place a permanent magnet over here, and this is a electromagnet over here? What will happen? This north pole will come here, south pole will come here, right? Now just assume that if this north and south pole both are rotating now, if both of them are rotating, this also will try to follow the lowest reluctance path. So it is somewhat similar to alignment torque only, but even if there is no excitation, still due to this flux connection, what will happen? Flux will try to follow the lowest path, and due to that it will generate a EMF, and that will generate a torque. Okay, so when there is a mismatch between the stator poles and the rotor poles, basically between the alignments, if there is no alignments, then this happens, right? Whenever there is misalignment. So here also if you see, there is bit of misalignment, meaning that let's say this north pole is here, this, like, it is a rotating magnetic field, right? So north pole will keep on rotating, so there is always a misalignment between the north pole and the between the north pole and the south pole of the stator, right? There is always a misalignment. So it is same like alignment torque only, but additional thing is, because the reluctance is different, so flux tries to follow the lowest reluctance path, so that's why it is called as reluctance torque. Okay, so this torque acts in the salient pole rotors with the stator field axis. Okay, so basically it's similar to alignment torque, but here the important portion, like the most important portion that you have to understand, don't worry, we will discuss about reluctance torque later as well. Okay, that here your relative torque will be proportional to 2 theta. How? If you see this, right, your reluctance torque is proportional to sine of 2 theta. It is not sine of 2 delta, right? So this excitation torque was proportional to the angle, sine of angle between the MMF, armature MMF, and the field MMF. Here the reluctance torque is proportional to angle between the sine of the field MMF and the armature MMF, but 2 times that, 2 delta. So that is a very very important property of reluctance torque. Okay, don't worry, we will understand about reluctance torque when we will study about reluctance motor in the last chapter. Okay, so these are the difference between the salient pole and the cylindrical pole motors. Okay, and these are the summary. You can go through whatever we have discussed. Same thing is written over here. So generally they are used, salient pole will be used in low to medium speed generators such as hydro generators, right, where torque requirement is higher than speed requirement. Okay, because for salient pole, right, for salient pole, high number of poles, high poles, it becomes very costly. So that's why we avoid it. It is easier to make more poles in the cylindrical rotor, hence the speed also is higher here. Okay, this already we have discussed in the first lecture of synchronous machines. Okay, so this was about the summary. So we have few questions. I will leave these questions as a homework assignment to you, and in the next lecture we will solve these questions, because already this lecture has gone very big. I don't want to solve. So in the starting of the next lecture I will solve all these questions. Thank you, and I will see you in the next lecture. If you did enjoy this lecture, make sure to hit the like button and comment down below your experience. Thank you and I will see you in the next lecture. Until then, happy learning.